The law of conservation of linear momentum is as important as the law of conservation of energy. It allows us to analyze collisions or problems with a change of mass better than Newton's laws. Before we discuss conservation of linear momentum, we need to discuss the center of mass of a system. This is because all external forces acting on a system will act as if the net force is acting on its center of mass. So let's look at a two-particle system, mass 1 and mass 2. And this is our x-axis. If we want to determine the center of mass for these two particles, the center of mass would be equal to m1 x1 plus m2 x2 over m1 plus m2, which is the total mass of the system. If we're looking at 3 dimensions, then center of mass of m is equal to the sum from 1 to n of mi xi over total mass. Center of mass in the y-axis is equal to the sum of all the masses from 1 to n of mi yi over the total mass, and the center of mass of z is equal to the same 1 to n of the sum of mi zi over total mass. Another way of writing that would be r equals 1 over m times the sum of mi ri as I goes from 1 to n. Now the above was for a number of particles in a system, but sometimes we actually have an irregular solid body, for example like a bat. Then it's not a homogeneous or regular system. So then we have to use a differential of mass to find the center of mass. So in that case, these equations in 1 will become x center of mass is equal to 1/2 the integral of x dm. Y center of mass is 1/2 the integral of y dm, and z center of mass is 1/2 the integral of z dm. That should be dm. So we're looking at slices of mass dm and then integrating it to come up with our center of mass of the entire body. Now if we have a uniform body, an object that has constant density throughout, we can use that to find the center of mass. So density, or rho, is equal to the mass per unit volume, or m over v, where v is volume. And if we solve for dm, we get dm is equal to mass over volume times dv, the change in volume. If we put that into this equation, we then get xcm is equal to 1 over v, the integral of x dv. Y center of mass is equal to 1 over v, the integral of y dv. And z center of mass is equal to 1 over volume, the integral of z dv. So this is a way of finding the center of mass for an object that, although is irregular, has the same density throughout. Now, there are some shortcuts we can take. If an object has a point, line, or plane of symmetry, then the center of mass will fall on that point, line, or plane. So you may not need to integrate and find the center of mass in all three axes. It may be obvious where one or two of the axes have the center of mass. Also note that the center of mass does not have to lie within the object. For example, a tire or a donut, the center of mass will be in the center where there is no mass. Same thing for a horseshoe. Now let's look at Newton's laws as it applies to a system of particles or a solid body. In that case, the net force or forces on that system or body would be equal to mass times the acceleration of the center of mass, where net force are all the external forces acting on the body. The mass is the total mass of the system or body, and acceleration is the acceleration of the center of mass of that body. So in other words, all the forces will act on a system's center of mass. And then we can rewrite his law as F net direction x is equal to mass times A center of mass in the x direction. Net forces in y is equal to the mass times the acceleration of center of mass in the y, and F net z is equal to mass times acceleration of the center of mass in the z direction. Now let's talk about linear momentum, which is given as p, and it is a vector. And p is defined as mass times the velocity. Its units are kilograms, meters per second. And if you notice that momentum is in the same direction as velocity. And if you apply F equals ma, you can derive Newton's second law in this form. The force is equal to the change in momentum over time. And this is important because this says that momentum only changes if an external force is acting upon it. Now notice I said external force. Internal forces that react within the system itself does not count. So for a system of particles, momentum is equal to mass times the velocity of the center of mass of that system. Because again, we assume that all the forces and movements work on the center of mass. Or you can write that the net forces on a system of particles is equal to the change in momentum over the change in time. Now we'll look at impulse and collisions. Impulse is how much force is applied over a certain amount of time. So impulse is given as j, and it is a vector, and that is equal to the amount of force related to time over that amount of time, and that goes from initial time to final time. The units for impulse is also kilogram meters per second, which is the same as momentum. And we know that with momentum, F is equal to the change in momentum with time. So that can also be written as F dt is equal to dp. So we get that impulse is equal to the change in momentum, which is equal to final momentum minus initial momentum. And this is the impulse momentum theory. And we can also say that impulse is equal to the average force times the change in time. So that's what impulse is and how it's related to momentum. So now we get to the law of conservation of linear momentum. Very important law. And notice I'm saying linear momentum because when we do circular motion, there's also conservation of angular momentum. So this is to differentiate between the two. And the law of conservation of linear momentum basically says if no net force acts on a system, then the momentum remains constant and the final momentum equals the initial momentum. So if no net force, then delta P equals 0 and final momentum is equal to initial momentum. We also know that your total momentum is equal to the sum of the momentum of each particle, which is equal to mass times the velocity of each particle. When we look at problems related to collisions, we will use momentum and kinetic energy changes to solve the problem. And there's a difference between the two. Momentum is basically an impulse or force applied over a certain time to reach an acceleration. Kinetic energy is work done over a distance to reach an acceleration. So momentum involves impulse and force over time. Kinetic energy involves work done over a distance. And the other thing to notice is because momentum is proportional to v and kinetic energy is proportional to v squared, that as velocity increases, momentum will increase, but kinetic energy goes up much more because the velocity is squared. So you can have a collision with a very slight change in momentum, but you can have big changes in kinetic energy involved with that collision. There are three types of collisions. The first type is an elastic collision. And during an elastic collision, kinetic energy is conserved. So kinetic energy final equals kinetic energy initial, as well as momentum final equals momentum initial. The second type is an inelastic collision. And with that, there is some loss of kinetic energy. And for example, that is through friction and thermal loss, or even the loss through sound energy. And the third type of collision is a completely inelastic collision. And in this one, two bodies stick together and form one body. So if you have mass 1 hitting mass 2, these end up becoming one mass 1 plus mass 2. And that is a completely inelastic collision. Let's look at an elastic collision in one dimension. So we basically have one mass hitting a second mass, and we'll call that the target mass and this the projectile mass. So we know that kinetic energy final equals kinetic energy initial, and momentum final equals momentum initial. Well, if you go through and you find the center of mass, and then you try to find the velocities, you'll see that the final velocity of the first mass comes out to be mass 1 minus mass 2 over mass 1 plus mass 2 times initial velocity of the first mass. And the final velocity of the second mass becomes 2 times mass 1 over the total mass times initial velocity of the first mass. And you can see how those are derived in your book. So if mass 1 equals mass 2, then we get V1 final is equal to 0 and V2 final is equal to V1 initial. So basically, mass 1 hits mass 2, mass 1 stops, mass 2 goes off in the same direction with the velocity that mass 1 had. Well, what if mass 2 weighs much, much more than mass 1? Then we find that whatever the initial velocity of mass 1 is, that is minus its final velocity. In other words, if mass 2 is so massive, the first mass will just bounce off it and go back in the opposite direction and barely move the second mass, whose final velocity is equal to approximately 2 times mass 1 over mass 2 times V1's initial velocity. And what if mass 1 is much greater than mass 2? Well, in this case, the final velocity of 1 is approximately equal to its initial velocity, and the final velocity of mass 2 is approximately equal to 2 times V1's initial velocity. Another equality in elastic collisions is that the relative velocity of the two objects stay the same after the collision, but in the opposite direction. In other words, if you have two masses, the final velocity of the second mass minus the final velocity of the first mass meaning the relative velocity, is equal to minus the initial velocity of the second mass minus the initial velocity of the first mass. So in other words, the relative velocities of the second and first mass is the same after the collision except for the opposite direction. Now let's look at an elastic collision in 2 dimensions. So in this case, we have mass 1 coming in and hitting mass 2. And let's assume that mass 2 is at rest. And then what will happen is mass 1 will go off in this direction, and mass 2 will go off in that direction. And we'll call this angle theta 2 and this angle theta 1. So again, we know kinetic energy final equals kinetic energy initial, and momentum final equals momentum initial. However, we have to apply this to both the x and y directions. So in the x-axis, our momentum is m1 v1 is equal to m1 v1 cosine phi of 1. That's m1 v1 final. This is m1 v1 initial plus m2 v2 final times cosine theta 2, because now we're looking at the x component of these vectors. Now in the y-axis, note that the initial movement of mass 1 is along the x-axis, if these are our coordinates. So we have no momentum in the y direction. So the momentum is 0 in the y-axis initially, and the final momentum is a minus m1 v1 final times sine theta 1 plus m2 v2 final times sine theta 2. Okay, and our kinetic energy for this problem is 1/2 m1 v1 initial squared is equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. So when you're doing a problem, we look at these equations, and we can usually solve for most of our unknowns with this technique. Now let's look at a system with a variable mass. And very often the example they use is that of a rocket. And the mass varies because as the rocket is moving through space, it's burning fuel, which takes some of the weight within the rocket and throws it out the back of the rocket. So not only does the rocket with fuel have energy and momentum, but the exhaust gas from the burnt fuel has energy and momentum. So you can apply the conservation of linear momentum and conservation of energy to the rocket, the fuel, and the combustion gases or the exhaust of the rocket. And from that we get 2 rocket equations. Okay, now if you go through the derivations in your book, you'll find an equation minus dm dt times v, velocity of the exhaust, is equal to the mass of the rocket times dv dt of the rocket. Okay, so the velocity of the exhaust is relative to the rocket. And this mass is the mass of the rocket plus the fuel. And dv dt is the acceleration of the rocket. So let's go through a few definitions that NASA has come up with. Minus dm dt has been labeled as minus r, where r is equal to the rate of fuel consumption. And mass times dv dt is equal to mass times the acceleration of the rocket. So if we substitute these in, we get r times the velocity of the exhaust gases is equal to the total mass of the rocket and fuel to start with times the acceleration of the rocket. And that is defined as thrust, or T. So this is our first rocket equation. And again, if you go through the derivations, you'll find that the final velocity of the rocket minus its initial velocity, in other words, the change in velocity from burning the fuel, is equal to the velocity of the exhaust gases times the log n of mi over mf, where mi is the original mass of the rocket with fuel, the initial mass, and mf is the mass of the rocket after burning fuel. So these are the rocket equations that are used to help send our people to the moon and back. And now we're going to work on some problems. Our next problem is: a vertical rod with a non-uniform density stands at position 0, 5 meters. Its linear density is given by lambda equals square root of y. What is its center of mass? Okay, let's diagram this problem. We have a rod, and if we call this x, we know this is at 0, 0, and this is at 0, 5 centimeters. And we'll call that axis y. And in this rod, we have a segment of mass dm. So going back to linear density, which is mass over a length of the rod. Okay, so mass over length, we know that that also could be equal to dm over dy, because the length is in the y direction, or dm is equal to lambda dy. So looking for the center of mass in the x direction, due to symmetry, is going to be at x equals 0, because we know the center of mass will be right down the center of that rod, which is at x equals 0. The center of mass of y is equal to the integral of y dm over the total mass, which is equal to the integral of 1 over mass times the integral of y times lambda dy from above. So that's equal to 1 over m times the integral of y. And we're given that lambda is equal to the square root of y. So that would be square root of y dy, or 1 over m, the square root. Now y, that's equal to y to the 1/2. So this becomes y to the 3/2 dy. And if you do that integral, you get 1 over m times y to the 5/2 over 5/2 from 0 to 5, the height of the rod. And if you go through this, you get 2 over 5m y to the 5/2 as y goes from 0 to 5. Or you get 2 over 5m times 5 to the 5/2, because we're substituting 5 in for y. Or y, the y center of mass, becomes 2 over m times 5 to the 3/2 if you do the math. Okay? Now, once again, we want to get rid of m from this equation. So we know that mass is the sum of the integral of dm, which is the integral of lambda dy, which is the integral of the square root of y times dy from 0 to 5, which becomes 2 over 3 times y to the 3/2 from 0 to 5, or mass is equal to 2/3 times 5 to the 3/2. And if we substitute that amount we found for m into this equation, so y, center of mass, is equal to 2 over m times 5 to the 3/2, which now becomes 2 over 2/3, 5 to the 3/2 times 5 to the 3/2. The 2's cancel out, the 5 to the 3/2 cancel out, the 3 comes up on top, and that comes up to the top, so you get y center of mass is equal to 3 centimeters. Or the total center of mass of this rod based on x and y is equal to 0.3 centimeters. Let's do some collision problems. A 50-kilogram boy stands on a raft which is at rest on a lake. The raft is 200 kilograms. The boy walks across the raft at a speed of 3 meters per second. What is the velocity of the raft while the boy is walking on it? So here's our water. We have a raft. We have a boy that is walking on it in this direction at 3 meters per second, and we'll call that the positive x direction. And the mass of the boy, we'll call mass 1, is equal to 50 kilograms, and the mass of the raft, or mass 2, is 200 kilograms. The velocity initially of the boy, mass 1, he starts at rest, so that's 0. His final velocity is equal to 3 meters per second. we know velocity initially of the raft of velocity 2 is 0. And we don't know what the final velocity of the raft is. So conservation momentum says momentum initial equals momentum final. So m1 plus m1 times v1 initial plus m2 times v2 initial equals m1 v1 final plus m2 v2 final. Well, the initial velocities of these are 0, so we get 0 is equal to 50 times v1 final, which is 3, plus the mass of the raft, which is v2, m2, times v2 final. Or v2 final comes out to be 150 over 200 with a minus in there, or minus 75.75 meters per second, and that's in the opposite direction that the boy is walking. Next problem is a 300 kilogram truck collides with a 200 kilogram van at an angle of 90 degrees. The truck was moving at 20 meters per second and the van was moving at 40 meters per second. The two vehicles stick together after the collision. What will be the speed of this single mass of vehicles and its direction? So let's say our truck is moving in this direction. It's 300 kilograms. We'll call that mass 1. And it's moving at 20 meters per second. And the van is moving in this direction. And that is 200 kilograms. And it's moving at 40 meters per second. And this is our x and y axes. So mass 1's initial velocity is equal to 20 meters per second. And velocity initially of mass 2 is equal to 40 meters per second. So if we set up our conservation of momentum equation, we get mass 1 plus the initial velocity of mass 1 in the x direction plus mass 2 times the initial velocity of mass 2 in the x direction is equal to mass 1 plus mass 2 times the velocity, the final velocity in the x direction. So if we put these in, this would be 300 times initial velocity of mass 1 in the x direction was 0 plus mass 2 times 40 is equal to, well, they stuck together, so the total mass is 500 times the final mass of that 500 kilogram mess. And if we solve this equation, we get 8,000 is equal to 500 times v final x direction, or the final velocity in the x direction is equal to 16I, meaning going in the x direction, meters per second. Now let's look at the y axes. Mass 1 times the velocity initial in the y direction plus mass 2 times the initial velocity in the y direction is equal to, again, mass 1 plus mass 2 in the final velocity in the y direction. So in this case, mass 1 is 300 kilograms, and it was moving in the y direction at 20 meters per second, plus mass 2, which was 200 kilograms, times 0, because it was not moving at all in the y direction. That's equal to 500 times V final times y, or 6,000 is equal to 500 V final y, or V final velocity in the y direction is equal to 12 meters per second. And we found V final in the x direction to be 16 meters per second. And this would be J, and this would be the I direction. So the final speed, V final, is equal to the square root of V in the x squared plus V in the y squared, which in this case would be the square root of 16 squared plus 12 squared, which is equal to the square root of 400, or a final velocity of both vehicles stuck together would be equal to 20 meters per second. And if we want to know what direction, well, we know that the tan of that angle will be Vy over Vx, which is equal to 12 over 16, which is equal to 0.75, or the arctan of 0.75 is equal to 36.9 degrees. That is the direction this final velocity will take from this collision. So that would be 36.9 degrees. Let's do one more collision problem. A mass moving at 10 meters per second hits an identical mass that is at rest. After the collision, each mass moves off at an angle of 30 degrees with the original line of motion. What is the speed of the two masses after the collision? Is kinetic energy conserved? Is the collision elastic or inelastic? So, diagramming this, we have a mass m moving at 10 meters per second, and it hits another mass m at rest, and both masses bounce after the collision at an angle of 30 degrees. And we want to know what is the speed of the two masses after the collision. So in the x direction, we say that mass 1, which is m, times its velocity of 1 in the x is equal to mass 1 times v1 cosine 30 degrees plus the second mass, which is a mass, times its velocity v2 times cosine 30 degrees. In the y direction, we do the same thing. The mass times initial velocity in the y direction is equal to mass times v1 sine 30 degrees plus mass times v2 sine 30 degrees. Well, we know that the mass initially is going in the x direction only, so v1 in the y direction is 0, so that becomes 0 is equal to this. So we end up with, from this equation, mass times v1 sine 30 degrees is equal to minus mass times v2 sine 30 degrees, which means that v1 has to equal v2, because these all cancel out. So now we know, because it's given that V1 is equal to 10 meters per second. So we know V initial is equal to 10 times now, since we know that the initial velocity of the first mass is equal to 10, we get 10 is equal to 1.74 times V1, or V1, which is equal to V2, is equal to 10 over 1.74, or 5.8 meters per second. So we just found V1 and V2. Now we want to know what the total kinetic energy is. Well, we know the kinetic energy before is equal to kinetic energy after, and that remains the same. So in this case, the kinetic energy before is equal to 1/2 m times V initial squared, which is equal to now we want to know if the kinetic energy is conserved, so we have to find what the kinetic energy is before and after collision and see if it's the same. So we know that the kinetic energy before the collision is equal to the mass times V initial. That's 1/2 mass times V initial squared. And we know that the total kinetic energy after the collision is equal to 1/2 the mass times V1 squared plus 1/2 mass times V2 squared. Okay, but we know that V1 equals V2, so this becomes mV1 squared. But from the equation above, we see V initial equals 1.74 times V1, or V1 is equal to V initial over 1.74. If we substitute that in here, we get mass times V initial over 1.74 squared, which is equal to V initial squared over 3.0. And this becomes 1/3 mV initial squared. So if we compare it to the kinetic energy before, which is 1/2. So if we compare the total energy before, which is 1/2 mV initial squared, to the total energy after, which is 1/3 mV initial squared, we see that it's less. So there was a loss of kinetic energy. Therefore, this was an inelastic collision. Therefore, this is an inelastic collision because the kinetic energy did not remain the same. It went down, probably due to the release of thermal energy from the collision. Let's do a rocketry problem. An Atlas rocket has an initial mass, rocket plus fuel, of m initial equals 3 times 10 to the 6 kilogram. After the fuel has been completely burned out, its mass is mf equal to 2.5 times 10 to the 6 kilogram, which is rocket without the fuel. burns the fuel at a relative velocity of V exhaust equals 60 kilometers per second. The rate of change of mass or fuel consumption is dm dt, which equals 1300 kilograms per second. What is the rocket's thrust? What is its acceleration? What times does the fuel totally burn out? What is the velocity at burnout? We're going to assume that the rocket is in space with no g-force acting on it. So its initial mass is equal to 3 times 10 to the 6 kilograms. Its mass after burning out the fuel is 2.5 times 10 to the 6 kilograms. Okay. The velocity of the exhaust is equal to 60 kilometers per second. And the rate of burning fuel, or R, which is equal to dm dt, is equal to 1300 kilograms of fuel per second. So we want to know what the thrust is, or T. Well, T is equal to R times V of the exhaust, which is 1300 times the V of the exhaust, which is 60 times 10 to the third meters per second, or thrust is equal to 78 times 10 to the 6 Newton. Okay, and that's a force. Now we want to know next, B, what is the rocket's acceleration? Well, acceleration is equal to force over mass, which is equal to, in this case, thrust over its initial mass. So that's equal to 78 times 10 to the 6th newtons over 3 times 10 to the 6th kilogram. That's equal to 26 meters per second squared. Now that's in space. If this rocket was lifting off, we would have to take into account the g-force, so the acceleration would then be the 26 minus 9.81, which would be 16.2 meters per second squared during liftoff, because it's feeling the effect of gravity from Earth. The next part is, what times does the fuel totally burn out? Well, the time of fuel burnout is the burning of the total mass of fuel, which would be mass initial minus mass final, over dm dt. So this becomes 3 by 10 to the 6 minus 2.5 times 10 to the 6 over dm dt, which we were given as 1300 kilograms per second. So that, if you go through the calculations, this becomes 385 seconds for the fuel to totally burn out. For the last part, we want to find out what the velocity of the rocket is after all the fuel has burnt out. So from our rocket equations, we know that V final minus V initial is equal to V of the exhaust gases times the log of the initial mass over the final mass after the fuel has burnt out. Or V final is equal to V initial plus V exhaust times the log of mi over mf. So we're assuming the rocket started from rest before the fuel ignited, so that is 0. So V final becomes 60 times 10 to the third times the log of 3 times 10 to the 6 over 2.5 times 10 to the 6, which is equal to 60 times 10 to the third times the log of 1.2, or the final velocity of the rocket is equal to 10.8 kilometers per second. Now that's in space where there's no force of gravity. If this was during liftoff, we would have to account for that in the final velocity. So we would subtract gt, the negative velocity due to gravity. So it would be minus 9.8. And the time we found till burnout is 385 seconds. So we'd get 10.8 kilometers per second minus 3773, which would equal to actually 7 kilometers per second. So that's taking account the force of gravity pulling back on the rocket.